Today in this class we are going to discuss about the path testing. Okay, a path testing is basically a method of white box testing. We have discussed till now those testing methodologies in the previous classes that were about the specification based testing, right? Black box testing, boundary value testing, then your equivalence class testing. All those testing methods that we discussed till now are the black box testing method. Now here, when we test the internal structure of the program, the control flow of the program, the way the program executes, then it is the white box testing. Okay, we are not only, it is not a black box, it's a white box, means we get the inside of the programs. Okay, so that is what the path, the first method that we will be discussing about is the path testing method. So as I am telling you, we can call it the code based or structural testing. Okay, so it is just complement of the black box testing, that is the specification based testing. Okay, and since it it explores the internal structure of the program, so it is basically based on implementation. Okay, and it contains lot of mathematical formulations like the program graph. Okay, that is the define use path. Okay, program slices, etc. Because we cannot at a time test the entire part of the entire project. Okay, so we need to consider one part of the program at a time. Okay, slice the programs. So, and this path matrix basically, or this code based testing basically is the basis for coverage matrix. Okay, that is, it explores every part of the program, that is every part of the program, that is the sequence of the execution of the program. Okay, so this is the basic overview of code based testing. Now, and as I was telling you, that is the usually is done at the unit level. Okay, directly it is not very helpful in identifying the test cases. Okay, and extensive commercial tool purpose. So when the program for which you are deriving the code based method of testing, if that is quite long, say more than 1000 lines of code, then it is not feasible for a person to do it manually. Okay, and there are extensive set of tools available for generating the test cases for these code based testing methods. So then every professional tester go for using a tool for generation of the test cases. So commercial tool support is there. Now path testing, see, the program is constructed in terms of a flow graph. Okay, from the flow graph we identify the path of executions. That is, we can call each of these paths as an independent path for the control flow. Okay, so we identify the test case, the way test case executes while it traverses the path. Okay, that is the test case execution we identify. If for the project, the program, if the number of paths is very high, very huge, then we adopt some method to simplify or to contract the number of paths. Okay, so some simplification mechanism is needed when the number of paths are very large. Now after that, it is the main problem of this kind of path testing is basically invisible paths. Okay, now what's an invisible path? So when those paths, which cannot be tested and verified some set of possible input values. Okay, if there is, with the possible input values, if the path cannot be tested, then that becomes an invisible path. And presence of invisible path basically leads to the creation of inappropriate test cases. Okay, so this is a hindrance or drawback of this particular method. Okay, so basically, because if there are some incorrect inappropriate test cases get generated, So obviously it leads to some incorrect and undesirable testing of the system. Okay. So we do not have, when we do not have in the possible set of input values for some part of the graph, then it is a infeasible path and is a problem for this particular testing mechanism. The big question here is when we generate the test cases for the path, what kind of faults, to understand that what kind of faults that is associated with that particular path. Okay, so that is a big question that must be addressed through the white box testing. Okay. Now, program flow graph, or we can simply say as the program graph. What is a program graph? Okay. So, a program graph is a graph in which every statement of the program, from the first statement to the last statement, are indicated by a node, and the sequence of program, that is the sequence of statements in the program. Suppose the statement I, statement, then comes the statement J, then comes the statement K, are connected through the edges of the graph. So the statement of the program indicates the node. The sequence of flow, or we can say flow control, is indicated by the arrows or edges of the graph. That is called as the program flow graph. Okay. So if node I, if the statement I comes before statement J, then there will be edge from I to J. Okay. That is what is the program flow graph. Okay. So when we determine a particular code with such sequences of the nodes and edges, it becomes the program flow graph. Okay. So it's a very, actually to identify those is not a very tough problem. There are some basic sequence of you can say basis test codes which identifies those, actually the if then else condition, the loop conditions. Okay. We can just insert those sequences in the graph, and you get the entire program flow graph for a particular program. So these are the four basic constructs which can be used to create such program flow graphs. Suppose if you have a if then else structure where you may have a single if then else, or there may be a if else later. Okay, it indicates the same kind of sequence. That is, if you have a if then else later, suppose if then else condition, you can basically use this kind of structure. That is, given a if condition, the node A indicates the if condition. Okay, given the yes condition, it goes through one path, that is, it goes to the node 2. Okay, given the else condition, it goes to the node 4. Okay, so if it is true, it goes to node 2. If it is false, it goes to node 4. Okay, and finally, after executing a certain sequence of statements, it converges in a particular node, which is the node 6. So this gives the if then else structure. Okay. Similarly, if you have the case structure, so case structure can have number of values, right, for depending on the matching numbers for that particular case condition. So when we have the case, suppose there are 3 different lines here in this particular example. So we can have this kind of structure. That is, with the node A means the case condition. Okay, if n equal to 1, it goes to the node 2. Okay, for the next case condition true, it goes to the node 4. Next case condition true, it goes to the node 6. So it traverses 3 different paths for n equal to 3. Okay, so ultimately, after execution of certain sequence, ultimately it converges in the n case, that is the line number 8. So it is the node 8 where it converges. Okay, so this is how the case constructs can be included in the program flow graph. Similarly, we can have the while loop. Okay, so while loop we can call it the pretest loop, where the condition is checked first, right? So when the condition becomes true in the node number 1, it goes to the next statement inside the loop, right? And that next statement is supposed to, and there can be number of sequence of statements inside that. Then there is now after the last statement, if it again checks the condition, so it goes to the number 1. Okay, if it is true, it will keeps on executing. Okay, if it becomes false, it goes to the 4. That is the exit the loop. Okay, so that is the flow structure for the while loop, which can be included in the program flow graph. Similarly, if there is the do while loop where the condition is checked at the last statement, So that can be shown through this particular flow structure. That is, the sequence will start from 1, then the number of statements inside this particular will be executed. It will be, condition will be checked in the number 3 statement, is the last statement, and then if the condition is, till the condition is true, so it will be basically keep on executing this particular loop, okay, do while loop, and then ultimately it goes to the condition number 4, that is the goes out of the loop, okay. So try to understand this program flow graph in terms of the triangle problem that we have discussed. What was the triangle problem? That is basically the problem where we try to identify the isosceles scalene equilateral triangle, right? Equilateral scalene and the isosceles triangle. So let us, before going into this part, identifying the flow graph, let us discuss little bit about the graph methodology. What is a graph one? So when we say, so I think you remember how does a graph is represented? That is, when we say a graph, something is like this, no? We have a sequence of say 1, it's a directed graph, right? 2, say there is a condition here, that is this particular node 2 here indicates the if condition, okay? If it is true, it goes to 3, if it goes to 4, okay? And then it converges to 5, okay? So there may be another which may not, okay? So this indicates a graph, right? So what is a degree of a node of a graph, okay? So when we say degree of this particular node is 3, because there are 3 edges which are incident, okay? So, and similarly we can have the concept of in degree and out degree. So here in degree means number of incident, or we can say incoming edges incident on that particular node. Out degree means the number of edges which are outgoing from that particular node. So for this particular node, in degree is 1, out degree is 2. Similarly, for this particular node 5, in degree is 2, out degree is 1. Okay, so this is what the concept of the graph here. Okay, so we can have different paths, which may be one path is from 1 to 7 directly going to the begin to the end. Okay, we can have actually, suppose here also, okay, fine. So it is then there can be another path, say, okay, 1, 2, 3, 5, 6, okay, then 1 and 7. Okay, so this is one path. Okay, similarly there can be another path 1, 2, 4, 5, 6, 1 and 7. So this can be another path. Okay, so we can have number of independent paths of execution of this particular graph. Okay, this is just an example graph that I am showing you. So here, when we consider this all the independent paths of execution of this particular in this particular graph, the directed graph, we get the basis set of executing paths. So basis set is all the independent. It is a set of all the independent executable paths. That is those independent paths which can be executed, and together it forms the basis set of execution for the graph. Okay. Now this is just for giving you the overview of how a graph is created for a program for execution. Okay. So going back to this particular triangle problem, for this particular triangle problem, see the number 1 is the name of the program, that is the program triangle. Number 2 statement is the declaration of ABC variable as integer. Number 4 statement is declaration of a Boolean variable which is a triangle. Okay. So these three statements, first statement, second statement, and the third statement, they are basically some form of declaration. So in the program flow graph, it doesn't have any role to play. So we are basically ignoring these three statements in the program flow graph. Okay. So our program flow graph starts from the statement 4. What is the statement 4? That is the output statement where you are outputting a particular string. Okay. So enter 3 integers which are sides of a triangle. So that is the fourth statement. Okay. So from there our program starts. That you can see the node number 4. After that, it takes the 5 statement, that is the next node is indicated by 5, which is nothing but input the values of A, B, C. Okay. From there, next statement is output side A is, that is the whatever you have whatever you have put as you have read from the keyboard, those values are being displayed on the screen using that. That's the three output statements, 6, 7, and 8. So 6, 7, and 8 comes in sequence in there. So 4, 5, 6, 7, 8 are the are the 5 nodes which are in sequence, because this does not have a control flow right there. It does not have a if-else structure or the loop structure there, right? So here it is. After that, the statement number 9 checks whether the triangle is feasible or not. We know that condition, that is, given any side A should be true, that is, any side A should be less than the sum of the other two sides. That is the basic condition for it to check whether is it possible to create a triangle using those 3 sides or not. Okay. So those 3 conditions must be true. That is, any single side should be less than the sum of the other 2 sides. So those 3 conditions are being checked, and that is done in the you see the statement number 9. That is the if structure. That's why you get 2 outputs there. One is if the conditions are true, another is if the condition is false. Okay. If the condition is true, then it goes to the statement number 10, that is, then is a triangle true? Is a triangle is as we have declared it as a Boolean variable, so is a triangle is true. Okay. Statement number 11, that goes to the other part, that is it is false, that triangle is not possible to create a triangle. And both merges in the node 12, which is the end if. Okay. That is the end of the if structure, where it merges. Okay. Then it goes to the statement number 13, that is, if creation of the triangle is possible, that is it true? Is triangle true? Okay. So if is a triangle, then again there is a if structure, that is, if A equal to B equal to B equal to C. So we know that if this condition is true, then this is an equilateral triangle, right? So it goes to the statement number, you can see is a triangle true, that is, it goes to the statement number 15, that is, the output is equilateral. So statement number 15, output is equilateral. Okay. There is another if statement inside that, which actually indicates that then it is an equilateral triangle. So it gives you the statement number 16, 15 is, then the output is equilateral. 16 is else, right? So this goes to the else. Okay. So nothing but this is also an if statement. So if A is not equal to B, A is not equal to C, and B is not equal to C. So this gives you the else if statement, that is the statement number actually 16. So it gives you the checking of this condition, that is, if all sides are not equal to each other. So if that is true, it goes to the scaling 17. Okay. If it is false, it goes to the other side, that is, it must be an isosceles triangle. Okay. And then it merges here in the 9, that is the end if, and there is another end if here. Okay. So if that statement number 13 here is not true, then it must go to the it must go to the 21. What is 21? Is not a triangle. Okay. And finally, end if of the 13 if statement, and it goes out of the program. Okay. So this indicates the triangle problem for this particular the graph for the triangle problem. Actually, while writing this code, there was a little bit a typing mistake where 16 went there. Actually 16 should be this line. Okay, so one line goes down from here. So 16 is this line, then 17, then 18, then 16 came here. So it is what is indicated for the sample program flow graph for the triangle problem. Okay. So that is what has been indicated there. That is, node 4 to node 8 are the sequences. The top level node 4 to node 8 are the sequences. 4 to 8 are the sequences. Node 9 through 12 are the if then else structure. Node 13 to 22 are the nested, that is the if else ladder, nested if else structure there. Okay, that is there is a nested if then else structure over there. Nodes 4 to 23 are the program source and the sync nodes. So it starts from the node 4, so that is the starting node of the program, and node 23 is the end node, or we can call it the sync node of the program. Okay, so since there is no loop exists here, so this is a directed acyclic graph. Okay. So the importance of a program flow graph is that the program execution corresponds to the path from the source to the sync node. Okay. So program flow graph basically indicates the program execution from the source to the sync node. Now, that is how the simple program flow graph, the program flow graph is being shown. Now, coming here is an improvement over that particular graph, which we may call it as a DD graph. Okay. So, what's a DD graph? The full form is decision to decision path. Okay. So, DDpath exists in the DD graph. Now DDpath is basically when we have some interior nodes, starting from initial node to the single node, where we have in degree and out degree both are 1, we can basically club them together. Okay, so in the DDpath graph, when we have such sequence of nodes, there may be a simplest DDpath is one node having one input and one output. One, that is for the nodes there must be in degree 1 equal to out degree 1. Okay, so for one particular node, one single input, one single output means one DDpath. Okay, so when we have such sequence of nodes, like initial node to the ending node, there are some interior number of nodes which are in sequence having the same type of structure, that is in degree 1 out degree 1. We can club them and make it one node. Okay, so that is, and when we do this, what happens? We always get a graph which comes from decision to decision. That is, those nodes which are having some, suppose the if then structure or the loop structure, basically the normal sequence are being clubbed into one. So those you get from one decision, that is one if then structure to another if then structure, or loop to loop. Okay, so we basically get the graph which indicates from decision to decision. Okay, so it is important to understand what is a DDpath. Okay, so this is a DDpath is let us consider, actually we need to consider three cases here to indicate the DDpath. Okay, so case 1 is the single node with in degree equal to 0. So in degree equal to 0 means the starting node where you don't have anything coming in. So in degree is 0. That is the starting node. And the case 2 is where we have the single node with out degree 0. That is the end node, sync node, where the program stops. Okay, you don't have anything going out there. Okay, so that is the out degree is 0. So Case 3 consists of those nodes, actually the decision node, where you have the in degree, either in degree or out degree greater than equal to 2. So that is only possible where you have the decision nodes. That is for those if statement or else if else statement, or in case of say the loop statement, loop condition checking, etc., where you can have either in degree is equal to greater than equal to 2 or out degree is greater than equal to 2. And for those consist of single node of the in degree and out degree equal to 1 are the simple statements in between, where one input is coming inside to that particular statement and one is going outside. So this is where you get in degree equal to 1 and out degree equal to 1. Okay. So after that, case 5 is the maximum chain of length greater than equal to 1. So those nodes which indicates in case 4 what is the length of that particular segment, that is starting from, that is indicated in the case 5, that is the maximum chain. I have already told you what is a chain. Chain is nothing but, in the previous slide, this is a chain, right? This is a chain of node where you have in degree and out degree 1. So case 5 indicates that maximal chain in a particular program segment. So where you have such statement where the case 4 is satisfied, that is though where you have the chain of nodes connected, where you have all the in degree is 1 and out degree is 1. Okay, that is the maximal chain. So that is indicated in the case 5. So that is what has been described in this particular slide. That is case 1 and 2 are the starting and the last node. Case 3 is the complex structure, complex nodes, where you have either in degree is greater than equal to 2 or out degree is greater than equal to 2. Case 4 is the short branches, where you have in degree is 1 and out degree is 1. And case 5 means the chain of nodes, where you have a sequence of such nodes where you have in degree is equal to 1 and out degree is equal to 1. That is case 5. Now given this DDpath, how do we create DD graph? Okay. So in this particular graph, for the triangle problem, you have a chain that is identified only from 4 to 8. So we don't get lot of completion here because we have, this particular graph is control intensive. There are lot of control statement. You see, you have a if statement there, you have a if statement here, you have a if statement here, if statement here, right? So there are a lot of control statements. Okay. So little sequence available. So there are some small DDpath. A DDpath exists here, a DDpath exists here, a DDpath exists here. These are all small DDpaths which cannot be shortened any further. So only one DDpath chain exists, and that exists in the first sequence, that is 4 to 8. You can see that above one, that is node 4 to node 8. So that is where the DDpath graph is created by combining those 5 nodes using the case 5 condition as the DDpath, and the rest remains the same. Okay, because there is no chance of large amount of compression here. Okay, but here is the DD graph. You can understand here the DD graph from this particular construct. So DDpath graph, as I was telling you here, that is the definition of DDpath graph is, given a program written in an imperative language, DDpath graph is the directed graph in which nodes are the DDpath of its program graph. Okay, and the edges represents the control flow between the successor DDpath. So in the DDpath graph, the nodes are not the single execution statement, but they are basically DDpath, and the edges actually controls the program flow from one DDpath to the another DDpath. Okay, so that becomes the DDpath graph. So in the triangle problem, you have lot of short DDpaths. Okay, so in this, the node 4 is the case of one DDpath and we'll call it the first. Okay. Similarly, node 23 is the case of two DDpath, that is the end statement. That DDpath here 1 means the case 1, right? And then case 2 DDpath is in the 23, that is the sync node, right? Then node 10, 11, 15, 17, 18 and 21 are cases of the 4 DDpath. That is case 4, right? So, and node 9, 12, 13, 14, 16, 19 and 20, 22 are the case 3 DDpath. So you check here, identify the different cases of DDpath, okay, in the program statement. What we get? The node 4 is the case 1 DDpath, node 23 is the case 2 DDpath, right? So from this particular graph, what are the case 3 DDpath? Case 3 where either in degree is greater than equal to 2 or out degree is greater than equal to 2. So what are the case 3 DDpath? Node number 9, node number 12, node number 13, node number 14, node number 16, node number 19, right? Node number 20 and node number 22. These are the examples of case 3 DDpath. Similarly, case 4 DDpath are the node 10, node 11, right? Your node 21, 15, 17, 18, right? These are the examples of case 4 DDpath. Okay? So, and so you get in the case 5, you get the control flow execution of the DDpath to DDpath. Okay? So you need to identify while creating the DDpath graph, you need to identify those nodes which form different different DDpaths, okay, using those case statements there. And then you need to connect one DDpath to another DDpath, okay. So those, you know, as those where you have the single chain, that must be one node in case of DDpath. That you must remember, okay. So this is what has been shown here, as I was telling you. Now, in the next statement, so as I was telling you, high quality commercial tools are available to generate a DDpath. If you have a program structure which is big enough, say more than 100 source line, then you can go for most of the tester, they go for the tools, okay, to generate the graph, DDpath graph, okay. So since the Tangle problem is logic intensive and computation is worse, so it basically is a combination of some short DDpaths, okay. So we don't get lot of reduction there. So take another example here. This is basically commission problem, path graph of a commission problem. In software engineering textbook, you find that what is a commission problem. Say to sell up to certain amount of money, the salesperson get a particular amount of commission. When he goes up little bit, he gets little more commission, and sells more, even more in a particular month, he gets the percentage of commission events increase further. So suppose for the first number of sales that is fixed by that particular company, he gets some 10% commission on the sales product. So after that, if he does some additional amount of sales, say another $1,800, then he gets 15% of commission. So above there, suppose if he sells in a particular month even more than that, say another $1,000 he sells, then he gets 25% commission. So there is a commission problem. So we are not going to the detail of the problem. Just imagine that there is a flow graph here. Okay, this is the flow graph for the commission problem. So to generate the DD graph, so you have to identify all the DDpaths. So one DDpath exists from 1 to 7. You see, this is the DDpath graph. So the first node indicates 1 to 7, that is one chain, right? Then there is another control flow, that is the case 3 DDpath exists in the 8. Okay, there is another chain which exists from 9 to 13. So that becomes one node. So there is you see there is a DDpath to DDpath. One goes from 8 to another node, 9 to 13, that is, and another from the 9 to 13 to back to 8. Okay. So there is another DDpath that exists from 8 to, that is DDpath 8 to DDpath, another chain that exists as the 14 to 19. That one, 14 to 19. So this becomes another DDpath chain, right? One chain that makes one node. So from 8 to that particular node, there is a connection, that is the flow DDpath to DDpath in the DDpath graph. It indicates an edge from one DDpath to another DDpath here. So it is from the 8 to the below node, that is 14 to 19. So from 14 to 19 it goes to 20. So there is an edge in this DDpath graph. So from 20 you get another chain. Because that 20 node is in the case tree. That is the if structure. So in the if structure there is one chain from 21 to 24. So that becomes one DDpath. Okay, so one node. So from there in the L structure it goes to 25. That is another that is the if structure. So there that is one DDpath. So from there it goes to another chain, that is 26 to 28. So this becomes another node. So given the condition true, it goes to this particular node. False means it goes to 29. Okay. Then it goes to the statement number 13. So there is another chain available in the below. So it is the 31 to 33. So this becomes one node in the DDpath graph. Okay. So you see that graph that can be compressed into this particular graph in the this becomes the DDpath graph. Okay. So it becomes a simpler graph compared to that graph. So number of nodes gets drastically reduced. It only indicates the flow from one DDpath to another DDpath. So DDpath can be one execution where you have the case 4 structure, that is one input, one output, or it can be the case 3 structure where you have greater than one or that is 2 or more inputs or 2 or more output edges. Okay, and of course the starting node and the end node. Okay, so that indicates the members of the DDpath graph. So this is what you get for the commission problem. Okay, so I think you have understood what is a path testing means. We have discussed about the basic flow graph, basic flow path, that is the flow graph, how to create the flow graph. Okay, right? And of course we have indicated the paths in those flow graphs, and also we have discussed about the DDpaths. Okay, that is how to create a DDpath from the flow graph, right?